Hey everyone, welcome to today's Explainer. Let's just dive right into this. Today, we're tackling a massive wall that pretty much every AI developer hits right after they build their very first cool prototype. We are moving way beyond those impressive but honestly pretty fragile toy AI projects. Instead, we're going to talk about how to actually architect robust production-ready AI agents. We'll be unpacking some seriously brilliant insights from developer Beam NXW, who recently broke down the 3 true pillars of agent engineering. So if you've ever felt completely overwhelmed by all the buzzwords flying around the AI space lately, stick around because we are going to clear all of that up right now.
Here is the architectural blueprint for our journey today. We're going to kick things off with crossing the demo chasm. Then we'll dive into harness, the environment, followed by loop, evidence-based cycling, and graph, explicit control flow. Finally, we'll wrap it all up with architecture synergy and diagnosis.
All right, part 1. Crossing the demo chasm, from toy to production.
To kick things off, we really need to shatter a super common illusion in the generative AI space right now. It's this idea that a raw language model alone can basically just act as software. The harsh truth is a naked model cannot maintain state across a long project. It can't run a test suite, it can't browse the web, and it certainly can't enforce your business approval rules. Which leads us to a really provocative question. Seriously, think about this for a second. Why is it that 2 totally different development teams, hitting the exact same underlying API, like the latest GPT or Claude model, end up with vastly different results? One team builds an agent that hallucinates its way into a corner and totally crashes, while the other team builds this rock-solid, reliable, autonomous worker. Well, the difference isn't the model's intelligence. The difference is that one team provided a stable workspace, heavily restricted permissions, and reliable tools, while the other team basically just crossed their fingers and relied on a really long prompt.
And that brings us to a massive paradigm shift. There's this golden rule from the source material that I absolutely love. Delete the model from your architecture diagram. The rest is the harness. This forces us to stop all this model worship and actually shift our focus toward real engineering. The intelligence of the model, that's just the engine. You still have to build the entire car around it. And that car is what we are calling the harness.
Which brings us to part 2, harness, the environment, the operating machine.
So agent harness engineering is all about building that operational machine outside of the model itself. If you've ever poked around the OpenAI Agents SDK or Anthropic's toolsets, you're looking at a harness. It's the runner that actually calls the model, executes the tools, handles the handoffs, and carries the state. Remember, a naked model literally forgets everything the millisecond a generation ends. The harness is the environment that actually gives your agent continuity, memory, and a real way to interact with the outside world.
If you're building a serious production-ready harness, you need a few non-negotiable components. You've got your context injection and your action services, meaning giving the agent access to things like a shell or a web browser. But crucially, you absolutely need persistence and execution control. The author uses Anthropic as a really great example here. Just compacting the context window isn't going to cut it for long, complex tasks. You need a harness that provides initialized files, full Git history, and strict incremental work discipline so the agent actually knows what it already did and what it still needs to do. Plus, without a solid harness, you can kiss any safety, governance, or observability goodbye.
Moving on to Section 3, Loop, Evidence-Based Cycling, the Mechanism of Feedback.
Loop engineering is all about designing the operational mechanism of repeated work. Look, by default, an agent using tools has this tiny built-in loop, right? It calls the model, sees a result, uses a tool, feeds the result back, and repeats until it hits a stop sequence. But true loop engineering happens when developers intentionally stack new cycles of observation and action on top of that base layer. It is not just throwing a magic while statement into your code, and it is definitely not prompt engineering. It is a highly deliberate, engineered decision about exactly what the system does after a model call finishes.
Now, this is a massive takeaway. You absolutely have to transition from a confidence-based loop to an evidence-based loop. The source highlights this as one of the most critical rules in all of agent engineering. Never ever loop based on an agent simply saying it's done. An LLM outputting, "I think I finished the task," is a terrible stopping condition. You have to loop on hard evidence. Did the test suite actually pass? Is the URL reachable? Did the JSON output validate against your strict schema? Did a human reviewer actually click the approve button?
To do this right, a proper loop needs a trigger, a highly specific goal, state memory, and a rock-solid stopping rule, like a budget cap or a timeout, so your agent doesn't spin endlessly and bankrupt you overnight. Keep in mind, every single time you add a cycle for a retry or a reviewer, you are adding latency and API costs. So the golden rule of thumb here is pretty simple. Only add a loop when the cost of a failure is greater than the cost of just verifying the work.
All right, Section 4, Graph, Explicit Control Flow, Mapping Complex Work.
So graph engineering is where we make the topology of the workflow explicit. We're talking nodes, branches, and state transitions. Think of popular frameworks like LangGraph or Microsoft's AutoGen. Quick clarification though, because this trips people up. This is not a knowledge graph that maps out entities and data relationships. No, this is graph-driven execution. It's about maintaining strict, explicit control over exactly which component is permitted to run next in a given sequence.
When you're doing graph engineering, you are the one making the highly tactical decisions. You're drawing hard boundaries to decide what gets handled by a creative LLM, what gets routed to a deterministic standard function, and where a human absolutely needs to step in. You're setting routing conditions and concurrency, deciding what can fire off in parallel and what needs to wait and converge. It is literally perfect for complex, multi-agent workflows where precise sequential control is a must.
But hold up. The author drops a massive warning here that we absolutely have to talk about. Building a graph before you fully understand the work is an incredibly expensive mistake. Look, it is super tempting to jump to a whiteboard and draw out this massive 30-node flowchart for your business process before you even have a basic agent working. Don't do it. If you over-engineer a rigid graph too early, you freeze your assumptions and make the whole system brittle. If your task is really just give an agent 3 tools and let it figure it out, building a graph is total overkill. Start lightweight, use a basic harness, look at your traces, and build from there.
And finally, Section 5, Architecture, Synergy, and Diagnosis. Let's bring it all together.
So, how do these 3 layers actually play nice together in the real world? Well, they fit together kind of like Russian nesting dolls. Let's imagine you're building an autonomous agent that researches and publishes a daily industry newsletter. Your graph outlines the macro steps, right? Research, draft, edit, publish. That graph runs entirely inside your overall harness. Now zoom in on the draft node of that graph. Inside that node, you might have an improvement loop. It drafts, it checks against a style guide, and it revises. And the harness is the thing providing the memory, the web browsing tools, and the evaluators that actually make those loops function. See? They aren't competing frameworks at all. They are perfectly interlocking layers of software.
Think of this as your ultimate diagnostic toolkit. The next time your AI system crashes or hallucinates, don't just blindly swap in a more expensive language model. Stop and look at the symptoms. If your agent keeps losing state or you can't even audit what it just did, you need to invest in your harness. If your agent is churning out messy work that clearly needs a do, check, improve cycle, you need to build an evidence-based loop. And if your workflow is getting complex and requires explicit human approvals, multi-agent parallelism, or deterministic branching, well, that's exactly when you implement a graph.
So I want to leave you with a provocative thought to take back to your own development team. Take a hard look at the AI systems you're currently building. Are you over-engineering a complex graph before you've even mastered your foundational harness? Remember, the raw intelligence of the model literally only matters if the environment it lives in is actually built for success. Start with a solid foundation, demand hard evidence over agent confidence, and only scale your complexity when the work actually demands it. Thanks so much for joining me on this explainer, and until next time, keep exploring.